So yeah, good morning, everybody, or afternoon for anyone on the East Coast. Welcome to our introduction to thermal mapping webinar featuring the Matrice 300 and the H20T series camera. I'll just do a quick introduction of myself. My name is Van. I'm the marketing manager and drone operator here at CanDrone.
And I'm Camille. I'm a solutions technician here at CanDrone.
And before we start, I'd like to just launch a quick poll to see how many H20T owners are here. So in a second here, I'm just going to launch the poll. You'll be able to quickly vote. It should be under the poll menu right here. And the votes are rolling in. Okay, it looks like everyone has voted here. So just quickly post a poll here. Awesome, thank you for voting. On the agenda today, so the objective of this webinar is to demonstrate how we collect and process thermal data into a radiometric ORTHOMOSAIC map. So we'll start off by doing a quick overview of the H20 series camera. Then we'll go into an introduction of thermography, followed by the data capture workflow, and finish it off with the data processing workflow with Camille. So in respect of your time, we expect this presentation to run for about 20 minutes with a Q&A session at the end. And if you have any questions throughout the webinar, please feel free to input it into the questions box as we go. They'll be on the control panel for your GoToWebinar, and we'll be happy to address them at the end. And a quick note, the webinar will be recorded and uploaded to our YouTube channel for future reference. So if you miss out on anything, you'll be able to replay it back just shortly after the webinar is completed. And as a final disclaimer, I'd like to acknowledge that thermography is a profession on its own, and we do recommend taking a professionally accredited course for infrared training from a training center like the Infrared Training Center if you wish to pursue this more seriously. So looking at the H20 series camera, apart from the standard RGB laser rangefinder and zoom features, we're here today for the H20T camera specifically. And to talk about the thermal resolution, this camera does have a 640 by 512 radiometric sensor with a focal length of 13.5 millimeter, which is equivalent to a 58 millimeter in a full frame camera. The thermal image format is in a R-JPeg format, which is proprietary to DJI, and we'll speak a little bit more about this later on in the presentation. As for accuracies, you can expect a plus or minus 2 degrees Celsius or plus or minus 2% accuracy, or whichever is greater when using this thermal sensor. So how does thermal imaging work? So thermal imaging cameras create an image from heat energy, and some of the core components are the spectral lens, thermal sensor, and processing components. The thermal sensor pixels are much larger than your typical image sensor, which is why you'll see that most of the thermal camera resolutions are smaller than the regular cameras. The sensor measures temperature by interpreting the intensity of the infrared radiation reflecting back to the sensor. And it measures infrared wavelengths, which are between 8 and 15 nanometers and is invisible to the human eye. You might hear terms like infrared, heat signature, or thermal energy, which can be used interchangeably when talking about thermal imaging. So for radiometric or non-radiometric, you might have heard these terms while looking for thermal cameras. There are two different purposes for these types of thermal sensors. So we'll start off by talking about the radiometric technology. With radiometric technology, this will allow the operator to capture and save images for analysis after the data is collected. With radiometric images, they contain quantifiable temperature data for each pixel of an image. This would be suitable for things like inspection work, where you want to be able to measure the absolute temperature value of a target. For non-radiometric cameras, they provide relative temperature information and not on a pixel level of data. This would be more appropriate for qualitative purposes, like visualizing the difference between the target and the surrounding areas, and would be suitable for situations like search and rescue or firefighting, where you want to be able to visually identify hotspots that could indicate a person in contrast to their surroundings. So you might think that I'll just point a thermal camera at a target and get an accurate temperature, right? Well, unfortunately, it's not as always as simple as it seems. There's a concept of emissivity, which is a major factor in the accuracy of your temperature measurements. And in short, emissivity of an object or surface can tell you how well it tells the truth about its actual temperature. So emissivity has a value that ranges between 0 and 1. And an emissivity value of 0 theoretically reflects all of its energy like a mirror, while an emissivity value of 1 would theoretically be a black body object that absorbs and reflects all of its energy perfectly. But in the real world, emissivity actually ranges from 0.01 to 0.99, as nothing perfectly reflects or absorbs energy. So errors in temperature measurements can occur in situations where you're measuring a highly polished metal object with low emissivity. This is where the temperature reading is actually reflected from another source of energy and reflected back at the sensor. So the example image below was borrowed from FLIR. The can, which has a highly reflective surface, reads at a significantly lower temperature than it actually is, because it's reflecting the temperature of the ambient environment. So what they did was they placed a black piece of tape on the surface, which helped to increase the emissivity and provided an accurate reading of the content that was actually inside, which was significantly hotter than what it was showing by measuring the reflective surface. So to the right, you'll see this is an emissivity chart from FLIR, which demonstrates the different emissivity values for certain properties. And a professional thermographer would adjust their camera settings to account for these errors. So in summary, the surface type can affect the accuracy of your measurements from a thermal camera. And as we said before, the topic of emissivity goes beyond this, the scope of this webinar, but we thought it was an important factor to understand in terms of accuracy. And as noted earlier, we recommend taking a professional thermography class. So some of the general best practices for thermal mapping are you want to fly as low as possible to the target. This will help to reduce the atmospheric conditions from affecting the overall accuracy of your data. Obviously, as you fly lower to the object, your data acquisition time will increase. So you need to use your judgment on in terms of efficiency of your data collection. As noted earlier, thermal camera resolutions are much lower compared to RGB cameras. And according to FLIR, you need a 3x3 pixels on target for qualitative detection and a minimum of 5x5 pixels to measure an object temperature accurately. To the right, you'll see a GSD resolution estimate for the H20T system flying on the M300. And currently, one thing to note is that the DJI application will not allow you to fly lower than 45 meters. You might be able to use other applications like UGCS to get a lower altitude. And for example, at 45 meter altitude, you can expect a GSD resolution of 4 centimeters. And on the higher end, at 120 meters, you can expect a GSD resolution of 10.67 centimeters. One of the key things to remember is that you can't accurately measure an object smaller than your GSD value. And in general, a minimum of 80% overlap is required for thermal mapping. We found that 85 to 90% work best for us when creating an ORTHOMOSAIC map. The time of day when doing a thermal thermal data capture is important. There's a concept of delta T, which is the difference between the temperature of the object and the surrounding areas. And this value should be the greatest when doing thermal mapping. So for example, when you're doing a solar panel inspection, it's best to do it during the middle of the day when the sun is at its peak. This will heat up the panels to their peak and will allow any anomalies to reflect and show up better in your data. For roofs, the surface must be dry and free of ice, snow, or standing water, and it's best to capture the data 1 to 2 hours after the sunset on a sunny day. One of the great features of the M300 is that it does have a safety beacon that will allow you to fly at night in most countries. And one final aspect to the data capture is you'll need to capture the data in a timely manner, because as the sun moves across the sky throughout the day, it'll create shadows that can affect the temperature readings as things cool down throughout your map. As for mission planning, the DJI pilot application makes it super simple to plan your thermal mapping missions. Some of the key parameters that we adjust are the camera type, the flight route altitude, and the overlap settings. So when you select the camera type, ensure that you have selected the IR camera within the H20 sub-menu in the camera settings. For this mission, we flew at 50 meters above ground level with an overlap setting of 85% for frontal and side overlap. The DJI application will automatically adjust the maximum speed, and in this case, it limited us to about 1.5 meters per second. So the data capture process was super simple. Once we planned the mission in the office and got onto location, all I had to do was set up the DRTK base station, power up the system, and ensure that everything is ready to go. And once it's ready to go, you just upload the mission and hit start mission, and it'll start to do the data capture. So during the data capture, I was able to toggle through the different color palettes of the infrared camera without affecting the final data output. And just make sure that before you start the mission that you have the IR zoom settings to set to one-time zoom only. The H20 capture captures RGB, thermal, and zoom data simultaneously. So just make sure that you have a fast enough memory card in the camera before you start your mission. So this data set that we captured was an abandoned school, and the area size was about 0.7 acres and took about 28 minutes to capture. And then we ended with about 518 photos in our data set. The data capture was done at about 10 a.m. On a cloudy day. And admittedly, this wasn't the best example, as the temperature difference from the surface and the building structure was very subtle.
So now I'm just going to take you guys through the steps needed to create a radiometric map. So first, download and back up your images. And then to keep things organized, separate out the thermal images into a separate folder, as well as the wide images can be parsed out into their own folder. And then secondly, the batch conversion of the thermal images is needed. And then we will go over the steps to take in Pix4D so we can stitch the images together, and lastly create the outputs. So, oh, I think we skipped one slide. Okay, for radiometric thermal mapping, you will need a more versatile photogrammetry software that can actually read in the Tiff image file formats. So we use Pix4D, but for non-radiometric qualitative thermal mapping, like Van had mentioned earlier, you could just use the DJI Terra software and import the R-JPEGs that come directly off your H20T SD card for qualitative mapping. All right, so what is a TIFF? A TIFF is a grayscale image that has editable pixel values. So TIFFs are not viewable by Windows Media Player. Rather, you would need to import a TIFF into a program like a GIS software to be viewed, like ArcGIS or QGIS. TIFF files require a large amount of storage space as well, and can be a challenge to share unless you zip them up. So just keep that in mind if you want to share your TIFFs. And then with the help of the EXIF tool community, searching online, there is a way to convert DJI's proprietary H20T R-JPeg file format to a TIFF. So we used an open access portable Python scripting tool, and the script essentially just looks into the folder with the source R-JPEGs and creates the TIFF with temperature values multiplied by 10 in a subfolder, but we'll talk about that a little bit more later. And the scripting tool works on Windows with a portable version of Python. And then after converting the R-JPEGs into TIFFs, we then used EXIF tools by Phil Harvey, also an open access tool, to run a command to transfer the EXIF location information from the R-JPEG image to the corresponding TIFF image. If you aren't comfortable with setting up scripting, Candrone does offer H20T R-JPeg to TIFF conversion services if you'd rather do that. So now we are ready to create an ORTHOMOSAIC in Pix4D. So we created our H20T camera profile using the camera model parameters for the camera found online. So I inputted the camera width and height at 640 by 512, and then I inputted the focal length of 13.5 millimeters and the pixel size of 12.79. Then I selected the thermal mapping temperature or thermal mapping template in Pix4D and ran the initial processing steps as well as the ORTHOMOSAIC creation process. So in total, to convert the images into TIFFs and then to process this small area in Pix4D, the project took about 30 minutes to complete. So here we have the final outputs from Pix4D. In the Ray Cloud view, you can see some camera positions that are red. These areas didn't process. This area is forested and at the edge of the project bounds. So it's likely that Pix4D had a harder time finding tie points between images in this area since it's really homogeneous forested area. So keep in mind that just like any other photogrammetry project, stitching any homogeneous area is difficult inherently to the software, and this is definitely amplified in thermal mapping as the pixels are larger and there isn't a great deal of variation. If there isn't a great deal of variation in your temperature, it can also pose a challenge. So this is one reason that it's important to use a high amount of overlap. So this heat map that you are also seeing here is being displayed in Pix4D using the index calculator tool. So here you can customize the indice values you want to highlight in your map, and you can also pan around and see temperature values for each pixel. And you can also play around with your mapping colors and your min and max values displayed. So the indice I made here was that I divided all the raster cells by 10. This is because the output from the R-JPEG to TIFF conversion gives Celsius values that are multiplied by 10, like I mentioned earlier. So by just applying some simple raster math, I can now see temperature values in Celsius and pinpoint specific temperatures of interest on my map. And Pix4D will output a TIFF of your thermal ORTHOMOSAIC. So if you're familiar with QGIS or ArcGIS, you can use those programs to create and analyze the customized thematic thermal maps. However, if you are not familiar with QGIS or ArcGIS, you can just actually use this Pix4D index calculator tool to do your map output analysis, which is simpler if you're not familiar with those programs. Additionally, you can process the RGB imagery outputted from the H20T wide camera as well, so that you can kind of have a reference against your thermal map to help depict objects better, since the resolution is quite a bit higher in your RGB imagery. So to process the RGB imagery, I use DJI Terra, but you can also use Pix4D or any similar photogrammetry software. And if you're looking to check and improve the accuracy of your thermal map, you can use ground control targets specifically for thermal sensors. So to achieve a good visibility of ground control points in thermal images, your GCP should have a low emissivity compared to the surrounding vegetation or other objects. So typically you would see aluminum plates being used or some sort of thermal specific GCP like the one depicted here with high contrast aluminum versus black cardboard. So that's can be used if you want to, increase your accuracy and have an accuracy assessment. And then I have another example here where we flew at 80 meters at a speed of 2 meters per second, and it took around 30 minutes to fly, and the resulting map focused on a narrow band of temperature values, highlighting inconsistency in roof temperature. So there are countless applications for thermal mapping, but in particular to thermal mapping, here are a few examples. You can do solar panel inspections to identify parts of buildings that are leaking heat and can provide targeted repair actions to reduce energy use and costs. Forest fire mapping is also a growing field in UAV thermal mapping. And lastly, thermal mapping is being used in precision agriculture to create thermal maps to detect temperature of crops and soil, which can be further used to estimate crop water stress and irrigation requirements. So that's kind of the conclusion of the content of our presentation. So I'll hand it back to Van.
All right, thank you, Camille. And thank you everybody for joining us today. We hope you found this information useful. So just note that Candrone is an authorized DJI dealer. We provide full service sales, training, and rentals. If you're looking to purchase a system, there is currently about a 1.5 week lead time for H20T cameras and M300s. So please visit our website, send us an email, and we'd be happy to connect you with one of our consultants. And yeah, now we'll open up for any questions. So please submit them in the question box here, or